Hello, everyone. Welcome to day three of the Water Summer School. Um, with that, let me introduce today's speaker, Tad. Tad is going to talk about how to create a differential model. Tad is a PhD candidate at Penn State University, working with Dr. Xiaoping Shen. Uh, Interestingly, his research combines artificial intelligence with process-based learning techniques, and as we'll see today, he has worked on explicitly on river routing tools. And he also works, I got to know, as a software developer at ERP and works on real-time flood inundation mapping. So thanks, Tad, for finding time in your such a busy schedule. And over to you.
Yeah, no problem. Thank you for the introduction. I always tell people that I have a hydrology problem, that I really need to get other hobbies besides doing all this stuff, but I find it fascinating and interesting. So I guess you have 2 hours with me where I get to talk about my hobbies. So I will share and get to work. Great. So as Debishi said, we're going to talk today about how to create a differentiable model. And for this talk, we'll go into specifically like a background on deep learning and process-based models and some of the similarities and differences between the two. What exactly is differentiable modeling? And there's a lot of terminology out there like physics-informed machine learning, physics-informed neural networks, or just physics-informed anything like that. So we're just going to differentiate between what this coding example is and what you might have seen in the past. And we're going to go into a coding example where we're going to go through some of my previously made materials, as well as go through how you can set up a differential model from the data inputs all the way to the experiment that you're running. And from that, we will go right into it. Oops. So just as a quick start to get me on kind of a page with everybody that's in the Zoom call right now, could you please post in the Zoom chat just like one word about your research? Like for me, I would describe it as computer science or something like that. So I'm trying to just figure out if I'm dealing with if there's a lot of hydrologists, process-based modelers, if there's a lot of deep learning experts, if there's people that don't do any hydrology, you could say nothing. So I just want to figure out how I can best convey this information to you. Okay, we got some geochemistry, contaminant reservoirs. Okay, that is I'm starting to get into reservoirs, so I respect your field very much. That's a really complicated problem slash thing to model. Remote sensing, undergrad. Okay, so it seems like we're kind of all over the place, which is good. So I'll try to be general, and there's some expert people in the room as well with some hyper modeling. That's good. Great. Thanks for chiming in. So just a little bit about me before we start, just so we can be a little more like a familiar level. So I'm a fifth-year PhD candidate at Penn State, and I'm in the MHPA lab group under Dr. Xiaoping Shen. I joined in August of 2020. So just maybe some people also had to deal with this, but the year or two of COVID graduate school was definitely a fun time for sure. So now I'm working as well at ERT as a software developer on the next gen contract. So this is the big pitch that the Office of Water Prediction at NOAA, National Oceanic and Atmospheric Administration, what they've been putting towards better flood inundation mapping. So that contract spans from better geo packages for modeling topography or modeling just riverine reaches. It expands to models and how you can better coordinate models and interoperability between them, as well as where I come in, which is taking the outputs of routed data and mapping it into some sort of real-time flood inundation modeling tool. So I've been doing a lot of that recently. And my background is actually not in hydrology at all. I'm a computer scientist. So I went to a small liberal arts college in Poughkeepsie, New York. It's actually right near the Carey Institute, if anyone's ever heard of that place or done any research there. But all my background was in computer science. And I rowed on the rowing team in college, and I really liked water. So I gave it a shot during an REU at the H.J. Andrews Forest in 2018. So the project there was on hyperreic flow and understanding potential drivers of hyperreic activity. It was a supervised machine learning task, so something where you needed to learn from data to best model processes. And it was similar to like random forest modeling. So it's using regression trees and just R in order to try and determine hyperreic flow. We didn't really figure out much, but I guess that's the whole fun of an REU, is just to goof off in the forest and get excited about hydrology. So enough about me. So I'll go into the background a little bit. So this is just another quick Zoom question. So I guess we already talked about this a little bit, but just a quick, like, a 0 if you use deep process-based models, and a 1 in the chat if you use deep learning models, just to see like how much everyone does. I'm guessing there's going to be a lot of zeros, considering that we had different like biogeochemistry, ecohydrology, remote sensing. Yeah, just as we thought. Okay, that's fine. I appreciate the zeros and I respect. Ooh, that's a good question. We're actually about to get into process-based models or deep learning models. So I appreciate the question there. Cool. So let's move into the next slide. So exactly into that. So a process-based model, apologies for a little bit of a blurry picture. I did my best with copying and pasting from previous PowerPoints just to get this all together. But process-based models are 1D or 2D solutions to physics-based equations, or they're just equations that are put together to represent ecological or geological, any sort of environmental process. So you could say if you have an equation for mapping storage of a reservoir, then that could be a process-based equation if there's a relationship between storage and discharge. If you're a remote sensing person and you're trying to understand evapotranspiration over a large scale, you might have a PET module, which is partially a process-based model. If you're doing soils work, you might use Richard's equation, which is a process-based equation. The list goes on and on, but essentially it's how we understand the world around us through mathematics and expressed in equations. So these process-based models often have a lot of complexity to them because of the data inputs that are required. So depending on what scale you're modeling, like hydrology it's a very interesting field because you could be modeling your river in your backyard, or you could be modeling a Hub 2 watershed or VPU. Like it's the scale of everything just goes from big to small very quickly. So in terms of just like complexity with process-based models, they really don't scale well. And additionally, as I said before, they're based on our understanding of the system. So process-based models are heavily influenced by human intuition and bias. And if you can tell, I'm being a little bit of like a devil's advocate towards process-based models, because that's the kind of the whole point that I'm trying to pitch of like, we have process-based models, we have deep learning models, why not a little bit of both with differentiable modeling? So moving from that side of the spectrum into deep learning. So deep learning is a collection of neural networks where there's multiple layers inside. So think of a neural network like, if anyone's ever gone through like the function box in elementary school, or it's you take input A, you put it into a box, there's some sort of function applied to it, and it comes out as output B. From there, the output will be compared against the target. The function inside the box will be tuned, and you keep redoing the process over and over again. The box is actually tuned via something called backwards propagation or gradient descent. That's a lot of calculus, though. I'll get into it a little bit later, but for now, just think of it as this magic box that has a linear component as well as a bias, like a y equals mx plus b. So deep learning is just stacking multiple of those boxes together so that you have the output of one box is the input to another. And because of the complexity that can arise from multiple weights and biases being added or multiplied together, you're able to end up getting this representation of a system that wasn't previous before. So you can either use machine learning, such as something like self-driving cars. So figuring out like, okay, is this a stop sign? Is this a log or is this a baby? You can use it for clustering algorithms. You can use it for prediction of time series. There's a lot of stuff you can do with deep learning. And it works directly with the data because you take data inputs, put it through a function, get outputs, and then the more data you have, the better your results usually end up being. This is just like a broad example of how you might use deep learning in hydrology. So say you have some sort of land surface model or atmospheric raster data or soil texture. Basically anything that you'd use in hydrology would be on those blue boxes on the left side of your screen. Then they would go into this box. In the example here is an LSTM, and which is just a type of recurrent neural network. So a network that takes in time series data, and you would get an output of Y, which is your prediction of soil moisture, stream flow, etc., whatever you want to get out of it. You then compare to your target, then all of the weights inside of said box would be tuned in order to get you a solution that's closer to what you want. And if anyone in the room has done any calibration before, this is very similar to how a model will be calibrated, where you will run many runs of the model in some sort of a calibration run. But the difference between calibration and like machine learning gradient descent is that calibration uses a global minima. So you're trying to find like the best possible number of parameters. So like you might have tens of thousands of runs, which take a lot of time and are very costly. But in machine learning, you're able to get a local minima. So you'll find a combination of models very fast that will probably be just as good as the global minima. And if they're not as good, the model will end up be able to overcome them and find a different local minima that might be a little bit better. So deep learning is just, as the quote says below, a chance to see what the machine can learn from all of the data. And this is just, as you can see, there's a lot of papers that are out about deep learning. It's a huge topic of information. There's stuff about dissolved oxygen, soil moisture, stream flow. The list goes on and on. There's review papers out. Neural hydrology is one of the most popular hydrologic GitHub repositories. It's a huge thing. And I think this is the last slide before I go into differentiable modeling. So I'll talk about this for a little bit and take a quick pause in case people have any questions. But just some limitations about deep learning is that training data have your resolutions. So your model is only as good as your inputs. Like the expression is called garbage in, garbage out. So with deep learning, if your inputs have resolution issues, if the accuracy isn't as good as you'd expect it to be, like say there's some biases that we don't understand, if you don't have the time interval you're looking for, if say you're trying to understand water usage in Colorado, where there's the Colorado River Compact, the availability of this data might not be there. So it's very hard to predict that. In terms of geographical imbalances, there's not many predictions in the Great Plains or like say Wyoming versus like New Jersey, like the Northeast, where there's tons of stream flow gauges or just predictions in general. Yeah, in terms of extremes, deep learning only can predict what it's seen. So if you have climate change happening and there's flood events that haven't ever been recorded, then your deep learning algorithm may not be able to predict them because it doesn't understand how to scale past what it's seen before. And the last thing is just capturing the non-stationarity of the data. So what happened, like how is it actually able to figure out clustering and understand what is going on with this data? So from what I've talked about before, there's pros and cons to both deep learning models and human process-based models and equations. And this is my favorite slide from my advisor. He pulled this picture from, I don't know if it's Overwatch or it's ChatGPT or whatnot, but we need hybrid models that can take advantages from deep learning as well as advantages from process-based equations that we've been developing for tens of, if not a century of hydrologic prediction. So at this slide, I'll stop just for a moment to see if anyone has any questions. Feel free to put them in the chat or even just put them in the Q&A. I'd be happy to stop and just take a minute to decompress about all that I've talked about.
So, Tad, we have one question, which is on
Yes,
the more data you have, the better the result, quoting Tad. Was he referring to large number of observation points or number of features?
that's actually a really good point. So there's been a lot of research into this in terms of features, and it honestly depends on if they're static features or if they're dynamic features. Because often, say you have just a random neural network. If you give it a lot of static features that don't have much variance, you're probably not going to get good results if you keep on just adding more and more static variables, especially because in like anything geological or even just hydrological static attributes are often correlated. So you could express land cover in 7 or 8 different ways that are all generally correlated. So if you just keep adding in attributes, you're probably going to reach a peak and the model will start to get a little bit confused. But in terms of dynamical forcings, where you have a lot of variance depending on the geospatial area, like precipitation, there's a lot of variance depending on where you are all over the country. Like temperature, atmospheric forcings, those generally, if the more you add, the better your model is. I hate to be that guy to be like, it depends, because there is a limit to everything. But in terms of answering your question directly, more data in dynamical forcings and over a larger and longer time range is generally better. Static values that don't change over time, more of those, you're probably going to max out after a certain number. So I think I used like 20, like in an LSTM I ran before, we used like 25. We could have added 50, but it wouldn't have mattered. Hopefully that was a good answer to the question, that you could take something away from it. We have
Yeah. So
another.
I think, yeah, so I think we can transition what you're talking on to a next question, which is pretty much similar. Uh, so will a typical rectangular So, is there a threshold amount of data we need to construct a model that is able to make accurate predictions of the phenomena? And related to that is another question. Will a typical rectangular data frame, say 30 rows, be enough to train a DL model?
So you could. So I'll start with the 30 rows.
Uh,
Um, so the less data you have, it's also the less confidence you have that your model is accurately representing the system. So if you can confidently say in 30 rows that you have enough data to represent everything that's going on, including the extremes, if you have, say if it's like temperature, if you have 30 rows that represent all the temperature ranges from your area, then you could probably get something away from it and you could get a valuable conclusion. But if it's just like for example, in my REU, we had 60 rows in a pandas data frame on hypereic activity, but it was at 2 streams and it was kind of all over the place. We didn't have enough information to truly understand the variability, especially because it was only at one site. So I'd say in terms of deep learning, you could figure out what does not work, but it'd probably be hard to interpret that. And I believe in the other question is like how much data is required.
Yep.
Honestly, I'd say just whatever you have. If you just take whatever you have, if say like you're doing stream flow, so I would pick like 5 different, like a precipitation, temperature, some atmospheric pressure, and then some attributes from camels. If those aren't enough and you think you can do better, then just keep adding from there. So I would probably just stick to whatever the LSTM papers have for their attributes, and if you'd like to add more, then add more.
Yeah.
There's no like, it's hard to like grasp exactly, especially like what field it is.
Yeah. So just a second, what you are saying, because we have folks other than hydrology. I mean, the number of rows, for example, as Tad is mentioning, it's more about how much variance are you capturing in your data. So, for example, if you're working not in a natural system like hydrology, but in a mechanical system where there are maybe fewer variances, you are working on a deterministic system, maybe smaller rows is enough as long as you're capturing the variance. Isn't it right, Tad?
Yes, that's good explanation of what I was saying. I completely agree.
Okay. For the timing, we don't have any. Oh, there's one more question if you want to take now. Um, what do you mean by hybrid? A combination of different parts of a model using both methods.
That's exactly what we're about to go into. What a great transition.
Yep. Okay.
So, in terms of hybrid modeling, we're going to talk about differentiable modeling, which we believe, and other, but my lab group, as well as a few colleagues, believe is one of the better, if not the best approach of physics informed machine learning. So, differentiable modeling is a hybrid in the sense that you use both things from process based equations as well as neural networks. So, if you look at this blue chart, it's a little bit of Microsoft Word math for you, but you could see that there's at least similarities between what is done in purely data driven neural networks and process based models. You have a function y, or you have an output y that is the result of some function applied to inputs. And the function has some sort of variables inside of it that are either minimized through calibration or minimized through gradient descent. So they're similar approaches to the same result, or they're attempting to get their same result. And in terms of both, like differentiable modeling as a whole, from what I'll go into next, is basically like, think about, you have your process-based model that is meant to represent a system. Say I'm a water quality person and I'm trying to understand, say, contaminants in my system. You might have a process-based model that's really good at understanding contaminants in a particular system and with a particular data set, but it's a tough time expanding. Or you could use a machine learning approach, which could be applied everywhere that you have data and is very broad, but it might not be able to find the optimal solution. So differentiable modeling is a constraint on machine learning where you use your process-based model to actually be that function in the middle, that box. But it's also an expansion of process-based modeling because you're able to reach more of a domain and update intermediate variables with neural networks. You're able to update your knowledge and learn from variant relationships and data you didn't understand. So this is a little bit of a calculus class. I'm going to try and keep it brief because we're not. It's 6 p.m. In Central Time, 7 p.m. No one wants to take a calculus class at Wednesday at this late. But essentially, how differential modeling and neural networks update the parameters is through backpropagation. So if you have some sort of equation, E equals A times B, any like say you have a parameter inside of here that's tracked, all operations on that parameter will technically have a gradient associated with it. So it's like literally like taking the derivative of something. So the more operations you put on that parameter, the more those gradients stack up. And eventually you use one giant integral or like auto differentiation to calculate how your weight should be tuned. Apologies, I'm trying to explain this just as the most generic that I can, but I implore you that if you'd like to know more about auto differentiation, to look at some good videos on YouTube about it, because they can explain it a lot better than I can with the detail it deserves. But all you need to know from this slide is that neural networks work by tracking operations. And so usually those operations are inside of a closed box where you don't understand what's going on. It's some sort of architecture that a smart guy working at Facebook or OpenAI developed. But with differential modeling, what if we used the physics equations that we know, like the Richards equation shallow water equations, some sort of geological equation. If we coded those up in a differentiable coding language, then the operations we'd be able to track and then update our weights of our parameters based on the physics itself. So this is kind of a overarching flow chart of how this works. So say you have some data that's going into your physics model. Say it's like a simple y equals mx plus b. We don't know the m parameter of our linear system. So we would use a neural network to learn it. So the neural network would take in your data, it would calculate use some weights or biases, then it would calculate some value of m for you. Excuse me. Then you would run your y equals mx plus b. You could potentially add more neural networks if you like, and you end up getting this output that's out here in your loss function, which is, say, stream temperature, say it's whatever you're trying to predict. Then through this calculus, this backwards propagation, you can update your neural network based only on the physics that you're running. This will make a lot more sense in the coding example that I'll show later. But because you're actually, instead of like before, where you just have a function that spits out a value and then you change the weights, your function is determined specifically by the physics equation itself. So the only scope that it knows, everything that the model knows comes from the understanding of the physics. So you're able to, with more certainty, constrain your neural network to a physical scope where your parameters and your outputs are realistic. You know what's going on, and it's interpretable, and your physics models have access to new understandings that they didn't know before. So this whole flow chart is a little bit, it just, if you're confused about differential modeling, I suggest you go back to this flow chart or even some of the coding examples just to show how it's not as complicated as the calculus makes it end up being. So this is just a quick slide of, if you've ever heard of PIN, mass conservation within neural networks, or physics-informed ML, how is all of this different? So with the same colored boxes, a physics-informed neural network flips this. So instead of feeding a neural network with data, you would feed it outputs of a physics model, and the neural network would be some sort of a post-processor. So we think our solution is better because, unlike the post-processor that's limited to the inputs of the outputs of the physics model, differential modeling is basically just the physics model you know, but is able to have a different range of parameters that are tuned by a neural network, which we think is very, very promising. In terms of physics-informed machine learning, that's generally having a loss function that constrains the outputs of the neural network based on physics, but there's still no interpretability. We don't know what's going on inside this neural network. It could be using a bunch of negative numbers. It could be using just parameters that make no physical sense. We don't know because of the black box nature of a neural network, meaning that inputs go in, outputs come out. It's a black box. And the last thing is an MCLSTM is you have a neural network where there's some sort of mass component tracked within it. So these have been shown to work relatively well in the field. Like there's an MCLSTM out there for hydrology. However, you still have a black box component inside of your neural network, which is what we'd like to fix with the added interpretability of differential modeling. So just a quick break again, just for some questions, some thoughts, some comments. I want to see where I am in terms of, okay, we still have some more slides to go. But yeah, I'd be happy to stop and take a quick breather about hybrid differential modeling. I
So,
think there are some questions.
yeah, so a couple of questions. In the meantime, others are welcome to put in the questions. So one of the questions that I'm going to start with is, you said in the back propagation, all it calculates is the differentiable or the gradient, right? So if let's say there is a local minima, how does it get out of it? Does it use a stochastic gradient kind of thing, or is it something else?
Yeah, so generally there's a few problems that I you can go into. Like, you either have like vanishing gradients or you have local minima that's hard to overcome. One thing that people use is changing your loss function. So if you look back to this right here, your loss function, that essentially is doing all of your back propagation and your calculating of variables. And something that people use is this idea of momentum. So you have parameters that, the say it's early in your training, and you have large gaps between your outputs, meaning that the model knows that there's a huge error. It needs to make drastic changes to fix this. So your momentum would then carry it past the local minima, because even if the loss goes down by a little bit, there's still such a change in your, there's huge loss values in general. It's able to skip past it. You might see more of a local minima um, happening when you have like very, very low losses, but I think that's a whole different 30-minute conversation you could really dive into after. But essentially the answer is just use a atom or some sort of loss function with momentum.
No. Okay. Now I see a lot of questions coming up. So the first one is the neural network in slide 19, the flowchart, explainable and to what extent? And is there a specific yardstick for understanding how explainable the neural network is?
So in terms of like a measurable output, not really. You could guess how. So like in general with neural networks, you can kind of guess a relationship based on plotting things spatially, or you can try and do just perturbations. So change your inputs to see how sensitive your model is to different inputs, but you'll never really know what's going on in the inside. So I wouldn't say there's a yardstick. There's just methods to try and understand what's inside of there. A perturbation experiment means, like, say you're giving your model three parameters, you move one of those parameters to its exact maximum range and see how the model responds. You then move the model, you basically can take away a parameter and see how the model responds. So you could see if it's sensitive to things. Like my model, for example, is very sensitive to upstream catchment area. In terms of the neural network that's on this slide that feeds in how interpretable that is, the difference with differentiable modeling with this is that we know the parameter scope of what's going in. So if we have some relationship of data coming in and outputs going out, we're only predicting a small parameter that's more well understood than, say, like a complex thing such as like a time varying stream flow, or even like a water quality metric, or like dissolved oxygen or something like that, where we still have a lot. There's complex processes to get it. So in my case, I have a neural network that takes in spatial attributes and learns Manning's roughness. Manning's roughness is just a lookup table of values from ranging from like 0.01 to 0.15, where every single number is well documented. The processes to get there might be black box, but in terms of the output, it's a lot of more of a simpler variable. So you don't have to put so much emphasis on the interpretability. I think that's my best way to explain it. I think there's
Yeah.
still some more questions coming in.
Do you want to take another one?
Yeah, I'd be happy to. I only have like maybe 6 or 7 more slides in terms of
Okay.
this. I just had a lot of coding materials.
Okay, so let's take another question. I think somehow you touched upon it in your previous explanation. This perturbation experiment you're talking about, also known as, I think, sensitivity analysis that people
Yes.
used to do. I think the other question is very related to that. Could you do a comparison between physics-informed black box model and the regular black box model? I think, or I think the regular neural networks, if I'm
Yeah.
getting it right.
Yeah, there's papers that are out that right now. One of my colleagues, Depeng Feng, it has a differentiable version of HBV, which is I'm not going to attempt to pronounce the name because it's very Norwegian and there's a lot of vowels, but it's a bucket based model, meaning that it's really simple. It's rainfall goes in. If the rain falls over an amount, it spills out of the bucket. Water stays in the bucket, has storage. Using differentiable HPV, we're actually able to come very, very close to that of black box LSTM models. And the difference is you're able to add a significant amount of interpretability where differentiable HPV parameters, they make sense geologically or geospatially. So the parameters will be different depending on your climate or where you're actually giving predictions, and you're able to really understand more from the model. So you may lose some steps in your predictive power, but it's not enough that it's going from some state of the art to very good, but you're gaining interpretability, which is something that people are very excited about. You're able to better understand how your outputs make sense or how your predicted values make sense in a geospatial as well as temporal setting.
Hmm. Okay. One more question is, so when you were discussing about mass conservation, could you explain maybe in a simple term, how is this mass or any quantity, let's say, I think because it's neural networks, how is any quantity per se is conserved across from the input to the output? Uh,
So the idea of mass conservation comes to like keeping track of your water balance. So and I hopefully I'm not too deep on the hydrologic content for those who aren't hydrologists on here, but mass conservation means that if you have a stream, say you have a bunch of water that goes in, eventually all the water has to go through the stream. That's the idea of mass conservation. It's a way that hydrologists can quantify if their results are correct because the water as the input eventually has to go out and run off somewhere or be discharged somewhere. So having a mass conservation element is just a representation of state. So you keep track of the state of inputs and you have to make sure that the outputs account for the inputs going in. So you're not just making up a whole bunch of like say you have 10 inches of precipitation coming into your model. You can't just make up a ton of it and just output a flash flood somewhere or so that's like the idea of mass conservation is you want to make sure that all of the inputs are accounted for when your outputs are produced.
okay. And is it okay to ask another question here?
Yeah,
Maybe.
for sure.
As you were explaining, so correct me if I'm wrong, and if you're saying that the outputs of the physics-based model, any model, is being used as an input to the neural network, and then it uses so-called the observations to backtrack and calculate the loss, right? And sort of update the prediction. If I'm correct, that if this logical flow is correct, then what extra does that neural network learn? Because so it is learning something. It is learning that okay, there is a discrepancy between the model output, the physics-based model output, and the observations. But what extra is it learning in terms of maybe parameters or processes? What is it learning actually?
So I just to clarify, one thing is that you don't always like in this case, this slide right here, there's the output of a physics model to the neural network. But in cases like the one that I have and that I'm going to show in a flow chart coming up, there's no it's only data inputs into the neural network into the physics model. So what this intermediate neural network does, which I think highlights your question, is that it's an intermediate state that is learned. So say I'm trying to understand water usage in Colorado. I don't have the data for that, and there's no physics equation to learn that. But I can change part of my physics model to incorporate a neural network to approximate it. Over multiple rounds of auto differentiation and training my neural network, I can eventually come to a relationship between inputs and the output of what this water usage is. So then I can better understand is if it gives better predictions, then maybe having some sort of bias term or some sort of extra term to account for this phenomena is beneficial. So I think the biggest thing, it's interpretability that we talked about before. It's in your predictions end up doing really well, just in terms of very good, a little bit below state of the art, but very good. But you're able to also capture those intermediate processes. And because when you're back propagating through your model, it's everything is exposed. Like if you have a differentiable equation that's 1,000 lines of code, all 1,000 lines of those are tracked through line by operation. So you're able to take advantage of all of the physics model and what's actually going on to bolster your understanding of the system. So hopefully I sold it well enough to go into the next topic. I think in terms of, I can go through the next slides and then we can take a break because it'll be just about at the hour, and then we can go into the coding example.
Yes, let's.
Okay. Okay. So now just going into specifically how my research uses differentiable modeling is it's all, we call it differentiable Muskingum-Kunj. So Muskingum-Kunj is the river routing equation. So what that means is, well, I'll go into a little bit, but it's just, think about it, I just call it delta MC because it's a little bit of a headache to say Muskingum-Kunj over and over again. It sounds a little weird. So we published this paper in early 2024, but essentially it takes the equation on the left and does distributed streamflow modeling. So in terms of like how you actually predict stream flow, sorry if I go a little too deep in the hydrology here, but how most people predict stream flow is by using a lumped approach. So take this basin on this picture right here. If you want to predict the stream flow at the bottommost point, one thing you could do is you could take all the average precipitation for the area, the average temperature for the area, the average pressure, et cetera, and some land cover attributes or some dam information, and you can make a point prediction of how much stream flow is at this point. But something that's not represented is the ungauged areas upstream of said approach. Oh, thank you for the actual information on the Muskingum-Kunj equation. That U.S. Army Corps of Engineers website's great. So the lumped approach will only give you one prediction point, and that's where the observations are. So you don't actually understand how the water is getting there. So Muskingum-Kunj uses river routing to take in some inflow, so what water is going into your river stream. It takes the previous time steps discharge. It takes the lateral flow, so water that's coming in through either the ground or in the middle of the channel that's not coming from upstream, and it generates discharge at time t plus 1. So it's a sequential, explicit formulation of just a distributed routing flow. And because this inflow is coming from upstream, you can trace it from the downstreammost point all the way up to where there's no inflow anymore. So you're actually able to get predictions over a large area. So in our case, we have predictions over like 500 or 600 river reaches, which is something that you don't get from a lumped or averaged streamflow prediction. So in our differentiable parameter learning or differentiable modeling approach, we take attributes that are just static at the river reach scale, such as upstream area. So like how much water is coming from upstream. Is it a lot? Is it a little? With slope, elevation, sinuosity, how wiggly the stream is, and put those into a multi-layer perceptron. So this is a very simple neural network that just uses many layers connected to each other in an output. And we get a value of Manning's N, which is a friction. So how much, if there's like concrete, there will be a lower Manning's N. If there's trees in the reach, there will be a higher Manning's N, because it's all just a friction coefficient. and Q, which we call just a spatial variability term. So Q is just to represent that not all streams are the same. If you have a Q that's a value of 0, you're going to have a rectangular stream. So it looks like if you plot it on a 1D, so you'd have a rectangle. But if Q is higher, you end up having a more triangular river reach. We tried to just add some more heterogeneity into the equation because you can't assume that all rivers are the same because they're not. We then have our physics equation, which is in yellow, the differentiable Muskingum-Kunj equation, and that takes in stream flow predictions from an LSTM as its lateral inflow, so the water that's coming in through the ground or in the middle of the channel from any sort of precipitation or whatever inputs. You then compare them, you get your runoff predictions, and you compare them with downstream USGS gauge results. And then once you calculate your loss, so like the difference between your gauge result observations and your runoff and like a mean squared error, you then back propagate and you tune the neural network. So like I said before, the neural network takes in inputs and then everything that it goes through is all bound by the physics itself. So the equations, this equation right here, or for example, these C terms have relationships with velocity of the flood wave, how much backwater is being added to the river stream, how long it takes for water to move from one stream to the other. So those physics terms are what is actually making the predictions in the MLP, not just a bunch of random activation functions. So it's a differentiable parameter learning setup is another buzzword of how you could talk about it. So our study site is in the Susquehanna River Basin. So it uses HUC-10s. What a HUC is, it's a hydrological unit code. So it just means an area. The larger your HUC, the smaller your value is. It's an inverse relationship. So HUC-12 is the smallest HUC value. HUC-10 is a little bit bigger, and HUC-2 is the biggest of the units. So this is just composed of several HUC-10s. You could see by the outline here. And it also just defines a basin. So that all water that's in this HUC will eventually flow down to this point. So that's a little crash course on USGS or US Geological Survey terminology there. So in here, the largest river is the Juniata River Basin, which has an upstream drainage area of 5,000 square kilometers, which is a pretty big river by most accounts. It's not the biggest, but it's substantial enough that we can make this a study site. And you can see the CDF shows that there's a big variance in the drainage area, so how much water is accounted for in these hydrological units. And there's 8 USGS or US Geological Survey gauges that have observations of flow. So what we know is actually going on in the system. And we compare all of this to the downstream most approach. So when it comes to Muskingum-Kunj, we have predictions by an LSTM all over that give us the flow that's going in. And using this equation, we can route the flow from these upstream tributaries all throughout the river reach to go to the downstream most node. And so this is the output of the MLP when I mean that it actually learns from the data. So the Manning's N value is often used statically, meaning that there is one prediction of Manning's N for the entire river reach. So that isn't very representative if you say you have a large area and you want to add variability. Like how is it that the friction of a slow moving river stream in the mountains can be the same as a river that's going through a city? It doesn't make sense. So our MLP ends up finding this power law distribution of parameters where you have at this lower drainage area, you're able to see that there's a little bit of uncertainty because there's just so many predictions. But the farther you go on, the lower the predictions end up being, which makes sense because a lower Manning's N means the water's moving faster, and water generally moves faster when there's a lot of it and there's a higher discharge. So just meters cubed per second. So how much water is coming at you. So this actually makes sense with the literature. And you could see at log scale that it ends up being a in negative x linear negative linear relationship in log scale. So you can see how the power law actually works out. And there's no calibration required. This is all through training and auto differentiation. So it's very neat that we're able to actually get this. So I implore you to look more into our work if you like a whole ton of research on this. But I have a lot of coding materials that I'm happy to share with you just so that you can best, instead of me explaining it to you, we can go through some situations and how you can actually implement a differentiable river routing equation. And then if you wanted to make changes to anything, how you would make your own differential model. So
I think, Ted, we can get started.
here, just a quick walkthrough of how this is different than, because there's a coding environment this is forked from, but it's mostly different by this notebook here. Notebooks workshop, you have a river routing notebook right there, which is where we're going to be spending most of this time. In terms of just how this, zoom in, how this library and repository is structured, I tried to make it as easy to follow as possible. So you have DMC, which is differential Muskingum-Kunj, and inside of it, you have several repositories related to what you're trying to do. You have in every single setup of a differential model, you have some sort of data. Anything related to data creation is in the data directory. You have neural networks that take in some input and give you Manning's N. Those will be in the neural network side of things. In terms of the physics model, so there's only one in this case, explicit Muskingum-Kunj, that is inside of the physics folder. And last, the criterion is loss functions. So there's multiple ways of calculating gradient descent. So those are your error functions. And then lastly, your experiments. So what I mean by an experiment is, say you want to train a model, there's a training function. Say you want to train a single parameter rather than a neural network, there's a function for that. If you want to generate metrics, or if you want to generate fake data, it depends on what you want to do, but your experiments will be it'll almost be the verb of this. You take several tools and you do something, that's your experiment. So with that in play, let's just dive right into the notebook. So all of this data is available at Zenodo. This is actually the correct link up here. So this, inside of this directory, let's download it. Okay, I already have it. That's good. Saves a little bit of time. But let's just step through what we have in here. Let's go to notebooks, data, and DMC Juniata. Cool. So inside of here, there's a little README if people are interested in what each of the files is. So I refer to a river network as a graph because you have each river you could think of as like on a number line, you have points with different lines connecting them. You can treat a river as just many lines all connected by different points. So it's sort of looks like a root structure of a tree, or it's that kind of thing. So that's why I just call it a graph. We have a CSV to explain all of the edges, so how the rivers connect to each other. You have the G, so the graph connectivity, all the nodes of the river graph, as well as the predictions. So this SRB post-processing. And lastly, this matrix that maps predictions to the river graph. I'm not really going to go into all of this. So if you have questions, I suggest either reading the paper or deep diving on your own, because I think that's something we could spend a lot of time on itself. I think the biggest thing that I want to take away is predictions for the network are here. So what water are we routing through the river network? And inflow interpolated is just the observations we're comparing to. And everything else, there's a series of functions that will get you to the end goal. It's kind of the opposite of yesterday's talk, where it was focused so heavily on data wrangling and data cleaning. In this case, because we've already spent some time doing that and it's a little complicated, we're just going to forget all the data wrangling and just go to the outputs. So once you have the data set up, the first thing you're going to go to your global configuration settings and change your current working directory. So I believe I already did this, but let's just change it. So go into the top, DMC, configuration, and global settings. So we just have to change this directory right here to be equal to your user name and wherever this notebook is located. So just a quick side tangent on something that I think that is important with anyone who's doing environmental sciences. I noticed there's a lot of people that don't have a coding background. So they might know like what is a configuration? Why would you even need this? So all of my experiments, if I want them to be reproducible, they have different variables that are attached to them. In some cases, I might have preset values of Manning's N that I'm trying to just run to test my model. In other cases, I might be changing the shape of my river reach. In other ones, I might be changing what section of the river am I actually routing on. So if you want to reproduce your research, because at the end of the day, good research is research that's impactful but also reproducible, you need to have some sort of way to clearly define to your end user how you can do that. So I believe that the best way to do that is through the use of configurations. So I used, in this case, 8 different experiments against USGS observational data, and each of them all has fixed variables. We don't really need to go into all of these because everything's taken care of by these variables that will either map to your data process directory, your current working directory, or what else might you, or any of these like experimental hyperparameters. Another big buzzword. Hyperparameter just means a parameter that is related to neural networks. I wouldn't really think too much of it. It's a weird buzzword, but again, it's the configuration stores all of this. So in your code, you never have to change anything, or you never have to go back and find in line 50 in the third paragraph, there's one tiny thing you have to change every run. It makes it a lot simpler. So just change this current working directory to your own. Sorry for that side tangent on configuration files. So once that is set, we can actually go through the imports. So just a quick understanding of what's going on. This is a normal error or / warning. It doesn't mean anything. So I use the Hydra file or configuration manager. It's made by Facebook, and it incorporates logging as well as configuration management. So you're able to substitute all of these config files equally and make some sort of a hierarchy amongst them. It's very nice. Matplotlib is what a lot of people use. NumPy. Omega config is a way to represent configs as objects. So something that if you have a config value, you can just do like config dot value instead of having to use some sort of other notation. So that just makes running with config files easier. Pandas, and lastly, PyTorch. PyTorch is what I'm using for my differential modeling. There's other coding languages out there for neural networks, but the key to a differential model is you need to have some sort of language that can track gradients. So PyTorch can do that, TensorFlow, JAX, Julia, the list goes on. Even Keras, if you like. I don't recommend Keras just due to industry support. That's a whole nother side tangent as well. So we're, in this case, since it's a Jupyter notebook, we're making sure that our path can see where the differential modeling folder is. We then import our MLP, our neural network. We import our physics equation and the experiment that we're trying to run. So training a model and then capturing some sort of statistics along the way. And then lastly is just the data set and evaluation stuff. So we could honestly go through all of these, but I have some overarching ways to go through things here. So next, or the last part of step one is just initializing your config value. So in our case, we're going to be setting our epochs to 6, just so that we can actually see what's going on and not have to wait 50 epochs. But this is what your config ends up looking like. It's this giant collection of variables that represents all just differences in your situation. And it all lines up with this YAML file out here. If people are interested, I'm be happy to go to it later. Just you could message in the chat if you are, but there's a lot of coding patterns in here that I use, such as a factory pattern, service locators, strategies, etc. If we have time at the end, I'd be happy to go into the ideas of patterns behind designing software, but it's a little bit off topic of differential modeling. It's more of just how to organize your project for yourself. So let's move on to setting up your database. Okay, so a quick question, is any specific reason for only using 6 epochs? I'm only using 6 in this case, just so you can see updates and we don't have to wait until the end. Because if we used an optimal, in my case, is 50 epochs. We found that your epochs matter when so let's back up a little bit. An epoch is just an iteration. So if I run 1 epoch, it means that I'm running through the model 1 time. If I'm running 2 or 3, it's 2 or 3 times. So the more epochs you have, the more iterations of your model and the more times you're updating parameters. So in my case, we're using 6 just so we can have some iterations in between and we can see the updates in this workflow without having to wait 2 hours or so. So it's not necessarily an optimal solution, but I think in a demonstration setting, it makes sense. So thank you for the question. So just let's go ahead with setting up the data set now so I don't see any questions. So in my case, what I have organized here is a dates object, a normalization scheme, as well as data for both the inputs to the neural network and for the physics model, as well as my observations that I'm comparing to. So I like the organization of objects. In computer science, an object is a collection of data, whether it's just a collection of arrays, a collection of data frames. It could honestly just be for storing many variables or doing an operation. But an object is just, think of it as like a water bottle holds water and can tell you, if it's like an Nalgene, how much water is in there. An object is sort of the same thing. So I have organization for all of those, so we don't have to have these long functions to break out what time is it or anything like that. So just to make things a little bit easier, we're going to be going through each of these objects. So below is just, again, a reminder of the geospatial area that we're representing. So we have many river reaches, 8 USGS points where we have observations, as well as attributes that represent this whole area of Pennsylvania. So let's read the CSV edges so that we can actually see what is in our graph or our river network. So each river has a code or some sort of an ID. So say my river, it's just a unique identifier to describe what river reach you're using. So node 1 or river 1 goes to river 2, river 2 to 3, etc. That's how you generate connectivity between your edges. And so each river itself has a width, and this is in meters, an elevation in meters, slope, a drainage area, so how much water it represents, a total drainage area. So say if you take the water that's in this river and you take all of the upstream rivers, how much water total is represented in the system. Wiggliness, Z bank is the actual bank height of elevation of the stream, as well as the distance of each river reach. So these are just, before we talked about static attributes and how like things to represent the system that don't change in time, this is what I meant. So like a river width or so elevation is a great one. Elevation doesn't change over time. Like something is always going to be at the top of a hill. It's the hill's not going to go away. So it doesn't change over time. It's static. And going into the, I don't think I'll stop and take questions at the end of this section. So into the normalizer. So I included this in the data section because it's a function that interacts with data. So when you have data going into your neural network, it's been proven beneficial to normalize it into a smaller range. So that gets rid of some of the variability that needs to be expressed by your neural network. So you normalize inputs going in. So say we have precipitation that's coming in anywhere between there's no rain or there's a lot of rain. You can scale that down through a min-max value function or mean standard deviation to keep the distribution of data so it all goes the same, but it's just between a constrained range. And that is very good for the neural network. So we have a normalization method that's done here. So then next we have a dates object that just creates a time interval. So what time exactly are we training on? In our case, it's 8 weeks. And then lastly, we have observations. So these are actually just USGS values of what's actually going on in the system at the downstream most gauge. So in this case, it's 80 meters cubed per second, which is a decent amount of flow. And I package these all together in this hydrofabric object. Hydrofabric is a generic term that just represents a collection of geospatial data. So that's just why I call it that. And then lastly, Torch puts it all together in this data loader object so that you can iterate through it in your epochs. So I think now's a good time. We have some questions to stop and talk a little bit about the data going into the differentiable model and the normalization.
Yep. So we have three questions here. First is, did you use any specific geospatial library for the map?
Oh, this is actually ArcGIS for Illustrator. It's a plugin that you can download. So if you have an ArcGIS license and an Adobe license, this comes for free. So all of this is from ArcGIS, and then I did some editing and manipulation in Illustrator. There's some tutorials on how to do it on YouTube.
Okay, and I think it's sort of related. Is the shapefile drone or satellite generated?
So these are all from shapefiles that are satellite generated. So these are HUC10s that you can pull from USGS's website. And the river lines are from the NHD 2.0 data set. That data set is not, it's getting like there's updates or different geospatial flow lines that are better, but because this work was started before all those products were out, I suggest using something such as Merit or TDX, but that's a whole nother conversation. But yeah, they're satellite images.
The next question is, what technique did you use in capturing the data in your data frame? Width, elevation, slope, bank height, etc. I think the data source is what is being asked.
Yeah, so I'm just going to pull up a table because I don't have the answer off the top of my head, but I can get it to you very easily. So these are all the data sources that we have. So it's Polaris, Modus, everything. I can post a link in to the actual paper in the chat, but it's all at the bottom, including direct links to the data products if you're interested. but they're all derived from publicly available data sets with citation and units.
That's great. And the last question, Tad, is what training would you recommend for DNN? I'm not sure,
Like,
is it training for learning DNN or is it training for training the DNN?
um, could you repeat the question? I assume DNN means differentiable neural network.
Yeah, I think so.
Was it would go the first part? Sorry, I was a little caught up by the DNN.
So the question reads, what training would you recommend for DNN? Learning, I think, for learning DNN.
Okay. Um, Honestly, I think if you'd like more information, I would search YouTube for videos on neural networks itself and deep learning. And then I would also get YouTube videos or some sort of courses on the physics. And if you honestly know the two of those separately, the differentiable neural networks and the whole process is going to be pretty simple because you're able to, like, say if you know how a neural network works, its ins and outs and the pros and cons, and you understand the domain that you're modeling, I think you'll have a pretty good time applying your range of skills into that area. There's currently not too many. There's a paper that I can send with more information. My advisor was the lead author on this paper, and I was the proud author number 27 of 30. It was a pretty big review paper, but this is for more information if you like on specifically differential modeling.
Okay, maybe
I
we
think it
can
now
move
is a
on.
good, yeah,
Yeah.
let's move on. So the next thing is the bread and butter of this presentation is actually choosing your model. So in my case, I have a few options where I can set my neural network equal to a power function and just try and learn, recreate a power function or just produce synthetic fake data. I can set my neural network to torch parameters, or I can, in my case, that what I'm going to do is use a feed forward neural network, so an MLP. And I'm also going to use my physics model, an explicit Muskingum-Kunj equation. So this neural network is embedded, meaning that it's passed in as arguments to my physics equation. So you have a configuration with all your variables as well as your neural network. And if you output it, you can see how you have an explicit Muskingum-Kunj physics equation with a neural network inside of it that's composed of the following information. So you have a linear input layer, so just the layer that actually takes in your information. You have multiple hidden states between the layers, and then you have the outputs, so the two variables we're trying to predict. So the Manning's N and the Q exponential term, as well as lastly a sigmoid function. This sigmoid function is, let me pull it up just to show visually what it looks like. But it's a function between 0 and 1 that never ends up getting to 1 and never ends up getting to 0. And what this does is it makes sure that your parameters or your outputs of the neural network aren't way out there. So if, say, my neural network predicted a Manning's N of 500 million, it would end up being 1 after the sigmoid function because it's bounded. So it's activation functions are used a lot in machine learning and neural networks. And you could talk a lot about activation functions as a whole, but sigmoid is just the one that I find is an output that works very well for machine learning. And so if in terms of creating your own differentiable model, this is the actual part that matters. You could have all of this data be the same, all your data sets, all the inputs, but changing this explicit Muskingum-Kunj is what actually matters. So I'll quickly go into that because that's the whole point of this. So this is my Muskingum-Kunj equation. So there's a lot of fancy ats and this and that. You can ignore that. That's just me trying to speed up processes. So I have many functions inside of here that are coded using PyTorch variables. So you're able to keeps track of the gradients. So division, exponential powers, clamps, so making sure the values are bounded as outputs. And this is the Muskingum-Kunj equation here. So remember QT is equal to C underscore 1 times inflow, C2 times inflow, etc. Excuse me, just like the equation from the presentation. And this is all of those coefficients calculated. And if you trace all of this back up, a lot of what this code is, which is why I don't want to go into too much of it, is it's all just data processing, data wrangling. But what really, in terms of differential modeling, that matters is your pipeline from you have your data, all of your operations in here are torch tensors, or they're TensorFlow, they're differentiable operators. So you can track these operations, which are what the neural network is tuned off of. So if we trace this back up here, this self.neural network, let's see where exactly, oops. Okay, so inside the neural network is where my values of Manning's N and spatial Q are being derived. So let's go inside of there. So if we look, these MLPs are generic, just so I can reuse them. But we have that same thing. We have a bunch of layers that are all combined together and an initialization function. The initialization function is there so that you can set your weights up for optimal training results. Because in machine learning, you use the weights are often randomized when you start up. So you have to set that state so you can reproduce your results. So we use that using initialization and fixing a random seed. So we have inside of this forward function, so this is what's actually called, you have your layers, so all your MLP, and then you denormalize from that 0 to 1 space into parameters that matter. So we actually have ranges of parameters for Manning's N, and you could see that in my equation functions right here. So my lower bound for Manning's N is 0.001, and my upper bound is 0.15. So my MLP actually knows this and can say, okay, my neural network gave me a value that's 0.33. That turns out in Manning's N, once denormalized, is equivalent to 0.4. So I can trace back later if we have questions, but just for the interest of time, we'll keep it moving. So again, when you're creating your differentiable model, the biggest thing is getting some sort of PyTorch class that inherits from NN module so that you can run forward your predictions in PyTorch. So now, lastly, let's choose our experiment. So the experiment we want is to train our model, and the experiment takes in a config file as well as a writer instance. I use TensorBoard. If you're not familiar, it's a way of visualizing outputs. I'm not going to go into it, but I'd be happy to post a link after if you're interested in learning about TensorBoard for visualizing machine learning progress. But this writer object also has my Nash Sutcliffe efficiency, or just my metric that I care about. It's the same thing as like mean squared error or R squared. It's just a metric that represents our understanding of how good a model is. And then we can run the experiment. So this will actually step by step put us through the Muskingum-Kunj river routing equation. And a lot of the stuff I've honestly spent more time in my coding career trying to make this function run faster and my data process reworked so that this didn't take 12 years to run all of it. It still takes some time. However, it ends up not being too bad. So I think honestly now, while this waits to go through its epochs, is a good time to stop and take questions and potentially talk through some more slides about tips for creating differentiable models.
Yeah, so please feel free to put your questions in Q&A. In the meantime, I had one question. So I might have missed, but how is it? So you said in between is that it's calculating both Q and N, right?
Yes.
Uh, so because the equation itself, the Q is dependent on N, how is it able to sort of optimize it?
So
Yeah.
yeah. So there's basically there's I don't like to ever admit we made a mistake, but in terms of naming things, having discharge be represented by uppercase Q and a lowercase q being a spatial coefficient was probably not the best idea. So I'll try and refer to it as Q spatial if that helps. So we have a neural network that learns a spatial coefficient that is not discharge related. It's more of a representation of um, river channels. So both are related in the sense that they both are in the same equation, but they play different roles. So it's more like it's a different part of the equation where you can tune two sides of it. You can either tune the channel dimensions or you can tune the friction that is able to predict the water going through the river. So apologies if people got confused about that. That was a comment by reviewers during the reviewer round, but as scientists are, we're stubborn. No changing variable names ever.
Yeah, okay, that makes it clearer. And the second thing is, again, I might have missed it, but did you talk about explicitly writing the equation somewhere, or is it not required? I might have mistaken that.
So say you want to make your own differentiable model, you do have to write the equation somewhere. So let's just, while we have time, we can, we can go through the steps of doing that. So I think it'd be a good exercise. So let's call, I saw reservoirs before. Let's make a differentiable reservoir module. So this is like the fun of working all the time is that when you don't have the time, you get to do live demos, which is great. So when you're making some sort of like an on the fly differentiable model, the first thing you do is you import torch and you import torch dot nn as nn and you make your class. So let's call this reservoir nn dot module, and we need an init function. It's just self. And what am I missing here? Yeah, I always miss this super command. Sorry. And all we need is a forward. I'm not sure if anyone on call understands like interfaces or parent classes, but this representation here is that the reservoir module is from an NN, a neural, it's a child class of the neural network module. So it means it has to implement certain functions from the parent. So in this case, it's a forward function. Sorry, I can't type and talk. I can't walk and chew gum. And this forward function is where we actually put in the variables. So if I'm calculating reservoir storage and I want to learn a parameter, I would, in this case, pass in a neural network and I would save it. And this neural network is also of the nn.module type, similar to this. In Python, this doesn't mean anything. This is just type hinting. I'm doing this just so I can better explain what is actually being thrown around. And this also returns nothing. So in terms of the state as well. There's probably some storage in your reservoir that you want to model. So self dot storage, let's do lowercase, is equal to a tensor, 0. So in our forward code, let's say we get in some information about discharge, that is a tensor. We get some value of channel dimensions. And we want to return a tensor. Then some sort of a physics equation would be, oh, the other thing is we have our neural network parameters. So let's do that in here. So in our equation, let's say we want to predict the channel dimensions of a reservoir. I don't have the equation off the top of my head, but I can approximate just for this example. So let's say we want our channel exponent. Let's say it's like it's a power law system or something like that, or let's say it's like our depth. Yeah, that's a good one. Our depth is equal to neural network and then some attributes. This is going to be the output of the neural network that we use in differentiable modeling. Then from depth, we would provide some sort of function against it. So if we want to represent storage with depth, we would probably, and predict discharge, it would be depth storage times depth. This is probably wrong. That's going to get me a 0. Then say we want to do something with discharge to scale it. Let's set a scalar or like some value theta. Let's set discharge equals to there. And then we just return, let's get rid of this. And now we return discharge. This wouldn't work in coding because I don't have these exact attributes to give it right now, or there might be a syntax error. But essentially, by running some sort of module with many physical values, taking in neural network outputs, running it through some sort of physics equation that you think represent the system, and then a discharge and getting some sort of output. And I'll look at the trainer now so you can see how it looks. And then calculating like some loss function here or running loss dot backwards, you're able to update your parameters of the neural network and get better understandings of the system. So hopefully that kind of talked through how that would play into place. So in this training loop right here, this is like for every epoch in your range, you iterate through your data and you pull in the observations and the attributes for that data. You then normalize them or pull out normalized values, and then you calculate your neural network values. Then you generate your prediction from your physics model. So this is honestly the cheat code right here of how to do differentiable modeling. Set up some data pipeline, normalize your attributes, calculate your parameters, run your physics model to generate a prediction, eventually calculate loss. And that's how you go through the whole thing. Everything else after this is just writing parameters and getting predictions. And so it looks like this is still running. So I don't know if anyone else has any more. I'm going to quickly go through some what I found tips and tricks of common problems with this approach since we only have like 15 minutes left. So you often can get NaN gradients. So what that means is your gradients aren't a number, and that's usually a result of a bad divide by zero. There's your something is a NaN in your data set. You have gaps that you're of where there's no values. So just checking your math is a good way to overcome that and make sure you're not generating any numbers that through while looking through your math might be good, but when you calculate derivatives later, they don't actually make sense. If your parameters aren't updating, something that might happen is your parameters might not make it all the way through. So in this example, my neural network outputs go from the internal functions all the way to returning this function. Like everything, there is a clear path from neural network to loss where nothing's interrupted. So I would check your gradient chain to make sure that's all connected. And if your parameters aren't making any sense, then it could be a model network architecture. It could be your parameter ranges. So the values that are coming out of your neural networks aren't within the physical understanding. So I would try and check your output or maybe tune your neural network to see if you need to better understand nonlinearity, or maybe you need more hidden layers. Maybe there's attributes that aren't doing anything you can remove. So this is more of a choose your own adventure. And this is actually, I spend a lot of time trying to figure out why things don't make sense, because mostly things don't make sense, or else we'd all be published PhD or master's level researchers by now. So I think this is done running, or it's just about. Does anyone have any like last? This is pretty much where the coding tutorial ends, or as far as what I have prepared. We're pretty close to the end. I know there's some people dropping off probably because it's getting a little late.
We have one more question. Are differentiable models also hybrid models, or is there any distinct difference
Mm.
between?
Yes, so they are hybrid models. That goes back to my slide on like physics informed neural networks, PIN, or physics informed machine learning. So it's all like you could classify all of them as hybrid models. I think if you looked at hybrid models in other spaces, you'd see um, a lot of similar themes and similar the idea of passing gradients through a physics equation. So geosciences, we just have been calling them differentiable models in terms of a common marketing idea behind it. So people at least know, because hybrid's a little bit, it's great to explain to someone who doesn't know hydrology that it's a hybrid model. But in terms of hydrology, a hydrologist might question what hybrid model are you using. So this is differential model is a hybrid model. Yeah, in terms of that, this is still running, but I guess I'll just give my conclusions while that's there. Yeah, one thing that I'd like to just show, I think Swellum is still in here. I got a little picture of him right here, but I'd like to just thank everyone for attending and listening to my PhD thoughts. I'll be hopefully defending in October, so this I think is a good test of my verbal representation or understanding of my PhD research. So I thank you all for listening, and